Hello physics students, it's Mr. Steinerson and I'm here today to give you a quick demonstration about normal force. I wanted to take a few minutes and just talk you through some of the details and ideas around normal force. So I'm going to give you a quick demonstration with a scale. So I'm going to lift up on this scale and I'd like you to predict what's going to happen when the scale is tilted upwards. So the back end of the scale will stay where it's positioned on the table. However, the front edge of the scale will be lifted upwards. So make your prediction as to what will happen to the reading on the scale. Will it stay the same because we're measuring the same object? Will it increase? Will it decrease? So take a minute, make a prediction right now. Hopefully you've locked in your predictions, and I'm going to lift up on the edge of the scale, tilting it upwards. Watch carefully what happens to the reading on the scale. I'm increasing the angle, and I'm going to tilt it all the way up to the top, kind of rest it there. And notice the scale reading actually decreased. So notice when the scale is at an angle, the actual reading of the scale is actually less than what it was when it was on a horizontal surface. This can be explained when we take a close look at the normal forces. Keep in mind, as I draw the free body diagram for the phones resting on top of the scale, the weight force will be directed straight downwards. However, the perpendicular force now is acting at an angle. So we would have to account for the angle involved and note that the perpendicular force is equal to the normal force, or therefore the reading on the scale. Since the perpendicular is one leg of that triangle made from the downwards weight force and the parallel force, note that that is now less than the weight force of the phone. So therefore the reading will also be less than when the phone is on a level surface. So when I take it over to the level surface, same phone, but now reads a higher reading because the weight force is equal to the perpendicular force when it's horizontal. Okay, let's do a quick recap. We know that when the scale was horizontal, it gave a different reading than when it was on the incline. And the reason it's different is because of the scale is reading part of that normal force. Now, I know the scale is reading in grams, but remember, weight is equal to the mass times the acceleration of gravity, and therefore it's going to be a proportional measure of that weight force from the reading in grams. Now, we know that normal force is equal to the force of weight when it's horizontal. So the reading of the scale was 0.242 kilograms, or 242 grams. The weight of the actual phone, multiply that mass in kilograms times 10, and you get the newtons, so about 2.42 newtons. We know that when it's horizontal, that weight force has to balance the perpendicular upwards force, therefore the normal force, so they must be the same number. However, when it's on an incline, the normal force is no longer equal to the downwards weight force, it's equal to the perpendicular force. So normal force would be equal to this component of the weight force. Since it's a component, we know that that perpendicular force will be less than the full downwards force, because this would be the hypotenuse of the triangle. The legs would be smaller. In this case, the perpendicular force is about 2.03 newtons. Doing the same logic, we can take the mass of the scale, read in kilograms, times 10 meters per second squared to get the force in newtons. Hopefully this helps clarify a few things about normal force and why the normal force will be different when it's horizontal versus when it's on an incline. Thanks, and have a great day.